Hello and welcome to another college algebra lesson. In this video, I will be covering rational functions. What rational functions are, all of their attributes listed here, and how to graph them. So one thing that'll be very new for these rational functions are these ideas of asymptotes. And we will have two different types. We will have vertical and horizontal asymptotes. And I will go over that in a few slides. Let's begin. So what is a rational function? That's pretty easy to explain. Rational means fractional. So it's a function with an x in the denominator of a fraction. So here are examples for rational functions. You can see every single one of them has an x in the denominator, and that is what makes it rational. The other thing that is a little more technical about this is that the fractions have to have a polynomial in the top and in the bottom. So that just means no square roots, no fractional exponents. They have to have exponents that are positive in whole numbers or a constant term in the numerator and denominator. Let's move on to what the attributes of these functions are. So now I will start in with the attributes of rational functions and how we can find each of these attributes. So with this particular slide and the next one, I will be taking the functions from the previous slide with one little change here. This was a +3 on the previous slide. I'm going to make it a -3. And we will be finding x and y intercepts for all three functions. All right, so with this, there's a lot of space. I'm going to write down exactly how you're supposed to do all of this. So to find the x-intercept, you will set the numerator equal to 0 and solve. So that's the first step. The second step is you will write as an ordered pair. Okay, so why do we set only the numerator equal to 0? Well, technically, to find any x-intercept, you set the entire function equal to 0, like this. Then, because I have a fraction, I would want to multiply both sides by x squared minus 4. And if you do that, on the left side, you can see the x squared minus 4 factors will cancel. And with this side, you're just going to distribute a 0 to both of these, and you're just going to be left with 5x squared minus 2x minus 3 equals 0, which just ends up being the numerator set equal to 0. So to find x-intercepts, most of the time for an x-intercept, there will be just one. But if you have something quadratic, you may have to factor it, like this. And then you can set each factor equal to 0 to get x would be -3/5 and x would be +1. So that's the first step. The second step is to write these as an ordered pair. And since you know an ordered pair is x comma y, each of these values will be the x-coordinate in the x-intercept. So I'm going to say this, x-intercepts would be -3/5, comma, and we have 1, comma. Now the nice thing about x-intercepts is that the y-coordinate will always be 0. Because an x-intercept is where the graph crosses or touches the x-axis. And if you're on the x-axis from the previous video, the y value is equal to 0. So here we go, we have our x-intercepts. How do you find the y-intercept? It's another 2 steps. One, you substitute 0 for x. So you'll replace all of these x's here with zeros, and you'll simplify. The next thing you will do is the same step as above. Write as an ordered pair. I'm going to abbreviate OP, ordered pair. So what this would look like then is you would have 5 times 0 squared minus 2 times 0 minus 3 all over 0 squared minus 4. So this is 0, this term is 0, this term is... Any term that has an x is just going to turn into 0. So what we are going to be left with will be negative 3 over negative 4. And anytime you divide a negative by a negative, it ends up being positive. So from here, this is the y-intercept, the y value. So the y-intercept will have a y value equal to whatever you get at the end of your simplification. The x-coordinate here was exactly what we substituted in for x. We substituted 0 in for x, so x will be 0. So here are the x and y intercepts for g of x. Let's look at the other 2 functions. So for h of x, we can find the x-intercept pretty simply. Again, we can just set the numerator equal to 0. So that'd be 14x plus 4 equal to 0. And we can solve for x. Well, this would mean that x would equal negative 4 over 14, or more specifically and more correctly, negative 2 over 7. If you have fraction, you want to make sure it's always in the simplest form. So since this is an x-intercept, we know the x-coordinate will be negative 2 over 7 and the y-coordinate will be 0. So this particular function, h of x, only has one x-intercept. All right, finding the y-intercept, again, super simple. We can substitute 0 in for x, and for all of the x's, my bad. And we can simplify. So any term that had an x up here will end up being 0. So I have 0 plus 4 is 4, and in the denominator I have 0 plus 0 is 0. And this is bad. We cannot have a divide by 0. If you substitute 0 in for all of the x's and you get a 0 in the denominator, there is no y-intercept. And that's because you're not allowed to have a divide by 0. So let me come back here and just label this as the x-intercept. All right. So in the next example, I'm assuming that's f of x, yeah. We have the top, we can set it equal to 0 to solve for x. And you might be wondering, solve for x? Hey, there's no x. There's no x to solve for. What that means then is there will be no x-intercept. Next, for the y-intercept, we simply substitute 0 in for x, and we would get 3 over 0 plus 1 is 1. That is not y, that is equal to 3. There we go. And since this is the y-intercept, we know this will be the y-coordinate. and we substituted 0 in for x, so that would be the x-coordinate. There is the y-intercept. Let's move on to asymptotes. All right, for the next attribute here we have asymptotes. So what are asymptotes? They're lines that a graph approach. So we will have two different types of asymptotes. The first type will be vertical asymptotes, and they will be vertical lines, and they will have equations. These will be x equals some number. And you're allowed to have more than one vertical asymptote. And we will have horizontal asymptotes. And horizontal asymptotes are, as you can hear in the name, horizontal lines. And they will be represented by an equation of y equals a number. And in college algebra, you will either have a horizontal asymptote at 0, which would look like it would be on the x-axis. You would have a horizontal asymptote that is not not on the x-axis, like this one here. Or you will not have a horizontal asymptote. But you can only ever have one horizontal asymptote. It is impossible to have, again, in college algebra, it is impossible to have two horizontal asymptotes in the same graph. How do asymptotes work? Well, asymptotes are lines that a graph approach. So when I have a graph on this coordinate plane with these asymptotes, the asymptotes draw the graph toward it. And so we can have what I can call the asymptote hugging curve. The asymptotes pull the graph toward it. And sometimes you can cross a horizontal asymptote, but that'll only be a horizontal asymptote. And vertical asymptotes can never be crossed. So they're just lines that a graph gets close to. We'll go over why you cannot cross a vertical asymptote shortly. How to find vertical asymptotes, which I will abbreviate VA, and horizontal asymptotes, which I will abbreviate HA. Well, the vertical asymptotes are already simple enough for you to find. This is very akin to finding the restricted values from rational functions, or when we've talked about the domain of rational functions. Vertical asymptotes very much go hand in hand with the domain of a rational function. So to find vertical asymptotes, you set the denominator equal to 0 and solve. You must write a separate equation for each vertical asymptote. And that's important for technical mathematical reasons. If you want to know more about that, you're always more than welcome to ask. To find a domain for a rational function, you would set the denominator not equal to 0 and solve. Then you would write the intervals. And it is important to write out intervals for this for reasons that I get into when we start graphing. So that leaves us with horizontal asymptotes, and horizontal asymptotes are a little bit different. It's more of a memorize thing than anything else. So to find horizontal asymptotes, we have to look at the degree of the numerator and the degree of the denominator. If the degree of the top numerator is greater than the degree of the bottom denominator, we can informally say that this fraction is top heavy. And since it is top heavy, there would be no horizontal asymptote. However, if the degree in the top is less than the degree in the bottom, we can call this bottom heavy. And if a rational function is bottom heavy, the horizontal asymptote will be y equals 0. And lastly, if the degrees match, we would call this balanced. Again, all of these are informal. Then we would take the ratio of the leading coefficients and set it equal to y, and that would be the equation of our horizontal asymptote. Let's look at some examples. For this particular example, we are going to be finding the vertical and horizontal asymptotes. So to find the vertical asymptotes, all we have to do is set the denominator equal to 0 and solve for x. Since this is quadratic, you want to check to see if it factors, and it does. We can set each factor equal to 0 and solve for x. And this is, these equations represent the vertical asymptotes. And again, each vertical asymptote has to have its own equation. Do not write x equals -2, comma 2. They each have to have their own equation. Now, another way you could have solved this particular equation is by the square root property. Just to bring that back up, you can add 4 to both sides and take the square root. But again, each vertical asymptote has to have its own equation, leaving you with these two equations on the left. So I'm also going to throw in here how to find the domain. So the domain, we would set the denominator not equal to 0 and then solve for x, which would basically equate to taking your vertical asymptotes and just saying x cannot equal 2 and x cannot equal -2. If we just take the equal signs and turn them into cannot equal, you're good to go. So here are the restrictions on the domain. Now to put these in an interval form, the domain can be any real number except for -2 and 2. But we can use any number left of -2, in between 2 and -2, and to the right of 2. And again, it's going to be important to have the domain listed out. You'll see why when I go over the graphing. It is another thing to note that each vertical asymptote, or each restricted value, shows up in the domain twice. As long as you have them in the correct order, you're good to go. All right, let's take a look at horizontal asymptotes. What you have to do for the horizontal asymptotes is look at the degree of each side of the fraction. So in the numerator, we have a degree of 2. In the denominator, we have a degree of 2. Since they match, we would call this balanced. It is balanced by degree in the top and the bottom. Once we know that this is balanced, we don't need the degrees anymore, and the only thing we need are the leading coefficients. The leading coefficients in this case are 5 in the numerator and 1 in the denominator. So we will just divide 5 by 1, and we will get our horizontal asymptote to be y equals 5. For these two examples, you can pause the video and try finding the vertical asymptotes for yourself just by setting the denominator equal to 0, solving for x. You can find the horizontal asymptotes by comparing the degrees of the numerator and denominator, and you can find the domain as well. Give it a shot. So for the first function up here, h of x, the vertical asymptotes are both x equals 0, and x equals -4. When you try to set the denominator equal to 0 and solve, you see that split b factoring or normal trinomial factoring won't work because you don't have 3 terms. There are 2 methods that you can use when you have 2 terms. One of them being the difference of squares, and this does not help. We cannot use difference of squares because we have a sum. So we should try common factoring. You can common factor an x out of each term and then set each factor here equal to 0 and solve for x. That's how we got these 2 vertical asymptotes down here. Next, I want to look at the domain. So we can quickly jump to that x cannot equal 0 and x cannot equal -4. So we can be any number except those. So I know -4 is to the left of 0, so that has to come first in our intervals. So we can go from -infinity to -4. We can go from -4 to 0, and we can go from 0 to infinity. Again, noting that each restricted value shows up in the domain twice. Then for the horizontal asymptote, the degree in the numerator is 1. The degree in the denominator is 2. So we would go ahead and say that this is bottom heavy. And anytime a function is bottom heavy, that means the horizontal asymptote is y equals 0. And a lot of the very same things can be done down here for this last one. F of x has a vertical asymptote of x equals -1. I think that's pretty easy to see. If you set it equal to 0, x will equal -1. The domain here would be x cannot equal -1, which means in interval notation, we can go from -infinity to -1, and then -1 to infinity. Now with the horizontal asymptote, you can see here that the degree in the denominator is 1, but the degree here is going to be 0. The degree generally represents the biggest power of x. And if there are no x's, then there is no degree, it's 0. So again, we can say that this function is bottom heavy, which means the horizontal asymptote is really y equals 0. Every single time a rational function is bottom heavy, the horizontal asymptote is y equals 0. Now, with all of these examples that I've done on this slide and the previous slide, none of them have been top heavy. The clue that a rational function would be top heavy is if the degree in the numerator would be bigger than the degree in the denominator. And if that were the case, you would just write no horizontal asymptote. So if you find a function that is top heavy, it would be no horizontal asymptote. That would be your answer. And the reason I haven't done any examples like that is because pretty soon I will be graphing rational functions. And in this course, we don't cover what happens when the top degree is bigger than the bottom degree. All right, how do you graph a rational function? Well, we have to go through and we have to find all of the things that I've just gone over. We have to find all the intercepts and plot them. We have to find all the asymptotes and plot them. We want to find the domain and write it above the graph. So here's where knowing what the domain is important. We want to make sure that there is a point in each interval of the domain, and then we can draw the asymptote hugging curve trademark. And I'm going to use the functions that we have already looked at, or at least two of them, because we already know all of the information, and I will just go over how to graph some rational functions, as well as a couple new ones. All right, here we have f of x equals 3 over x plus 1. Now, I've already mentioned the most recent slide that the degree in the numerator was 0 and the degree in the denominator was 1. So we have a horizontal asymptote y equals 0. And you would go through and find the x-intercept, the y-intercept, the vertical asymptote, the horizontal asymptote, and then we would just put this all on the graph. So the x-intercept, there is none. So I will not put any points over here on the x-axis. However, we have a y-intercept, 0, 3. So I'm going to put the y-intercept there. We have a vertical asymptote at x equals -1. So all this is telling you to do is go to the x-axis, find the number -1, and we will draw in a dashed line. I'm going to make this a little bit bigger so you guys can see where the dashes are. So vertical and horizontal asymptotes are always going to be dashed lines. They are not really part of the graph. They are there just to help us get the graph into the right place. So the horizontal asymptote here is y equals 0. And y equals 0 is what the means the horizontal asymptote will lie on the x-axis. So there it is. There we have all of our information: x-intercept, y-intercept, vertical asymptote, horizontal asymptote. It's all represented on the graph here. Now the next thing I want to do is find the domain. And that goes from -infinity to -1 and -1 to infinity, just as we mentioned a couple slides ago. So when you find the domain, I want you to write it above the graph. So check this out. -infinity to -1 is over here, and -1 to infinity is over here. This vertical asymptote is where our domain splits into two parts. And I've got a great big union in between there. So again, the steps: find the x and y intercept and plot them, check. Find the vertical and horizontal asymptote and plot them, check. Find the domain and write it above, check. Why do we do that? We need to have one point graphed in each interval of the domain. So if you look at the domain interval on the right, I have a point there. It's the y-intercept, sure, but it's a point that has been graphed on this interval. Now when you look at the left interval, -infinity to 1, we're only looking to the left side of this vertical asymptote. Are there any points plotted over here? No. So you have to pick an x value to the left of -1. Let's pick -2. Sure. So you have to pick an x value and plug it into the function. And I'm picking -2 again because there's no point already plotted on the left side of this vertical asymptote. In this interval, we don't have any points plotted. So I'm going to take a -2, so that'll be my x. And I'm just going to substitute that into the function and figure out my y. So here, at -2 for the x, I get back a y of -3. So there's my point. Now, do we have a point in each interval? I have one interval to the right of the vertical asymptote, and there's a point plotted there. I have one interval to the left of the vertical asymptote. There's a point plotted to the left. We're good to go. We can now draw the asymptote hugging curve. And what that means is that from each point, so I'm going to start with this point on the right side over here, we just draw a curve that will get close to each asymptote. We're not going to cross any asymptotes, so I'm going to get close to this asymptote there. And I'm going to come down here like this and get close to this asymptote here. That's it. So from this other point on the left-hand side, I'm going to get close to this asymptote here, and I'm going to get close to this asymptote here. And that's it. That is drawing the graph. Let's take a look at a few more examples. Here I have a new function that we've not been looking at. G of x equals x minus 4 over x plus 5. Now again, to find an x-intercept, all you have to do is set the top of the rational function equal to 0 and solve for x. You'll get x equals 4. That is the x-coordinate for an x-intercept. The y-coordinate for an x-intercept is always going to be 0. To find the y-intercept, you substitute 0 in for the x's. So there'd be 0 minus 4, which is negative 4 in the top, and 0 plus 5, which would be 5 in the bottom, negative 4 over 5. Since we substituted 0 in for x, 0 would be the x-coordinate. Let's go ahead and plot those on the coordinate plane over here. So I've got the x-intercept at 4, 0, so that's right here. I've got the y-intercept at 0, negative 4/5, right about there. To move on to the asymptotes now. The asymptotes, the vertical asymptote is what you get when you set the denominator equal to 0 and solve for x. So if you set the denominator equal to 0 and solve for x, you'll get x equals negative 5. And the horizontal asymptote is based on the degrees. So here I have a degree 1 on the top and the bottom, and since those degrees are the same, we would call this balanced. This is a balanced function, which means we take the ratio of the leading coefficients. So 1 over 1 is 1. So the horizontal asymptote is y equals 1. The vertical asymptote is x equals negative 5. Let me get those graphed in here. And one thing I don't think I did in the last example was labeled my asymptote. I'm going to go ahead and label my asymptote. The horizontal asymptote is y equals 1. The vertical asymptote is x equals negative 5. And so you can just label it with a VA for the vertical asymptote and then the actual equation. Remember, you have to have an entire equation here, an equal sign, a variable, and a number. And the same thing similar for the horizontal asymptote. Horizontal asymptote HA with a little colon, a variable equals some number. Horizontals are always y equals, verticals are always x equals. Now we need to find the domain here, and I'm going to mark the domain in blue. So the domain is based on the vertical asymptotes, remember. Domain is based on the vertical asymptotes. So our domain here would be negative infinity to negative 5, union negative 5 to infinity. And this union, and I did not say this in the last example either, the union will be right above the vertical asymptote. Any union will go right above a vertical asymptote. So on this side, I know the domain for this interval is negative 5 to infinity, and to the left, I know the domain for the left interval is negative infinity to negative 5. Now I just observe. Do we have points plotted to the right of this vertical asymptote? Do we have points plotted in this interval of our graph? Yes, we have 2. Do we have points plotted in this part of our graph, in this interval of our graph? Any points plotted to the left of this vertical asymptote? Nope. So we have to find one. So all we have to do is pick any value you want. You can pick -6, -7, -8, -9. It doesn't matter, whichever one you like. I'll pick -9. Sure. So let's pick f of -9. So this will be my x-coordinate. And I'm just going to substitute the -9 in for the x's. Get -13 over -4, which is approximately 3.25. In this case, it is exactly 3.25. That's my y-coordinate. So I have an x-coordinate of -9 and a corresponding y-coordinate of 3.25. So I'm going to plot that point, -9, 3.25, right about there. Now, we have at least one point in each interval. I have a point in this interval from -infinity to -5. There it is. I have a point in this interval from -5 to infinity. We have 2. Now all we have to do is draw our asymptote-hugging curve, and we can be on to the next example. So I'm going to do my left interval first. It might look something like this and something like this. It's not perfect, but it'll work. And when you have 2 points in the same interval as we do here, we have to make sure they get connected as well. So we know for sure those are going to get connected. And then from there, this graph will get close to the horizontal asymptote and close to the vertical asymptote. And there you have it. There's the graph for g of x equals x minus 4 over x plus 5. Let's see what happens when more than one vertical asymptote is introduced. All right, for this example, we have yet another new function. So remember, you can find the x-intercept if you set the top equal to 0 and solve for x. Well, if you set the top equal to 0 and solve for x, you may notice that there are no x's to solve for in the top. Therefore, we have no x-intercepts. To find the y-intercept, what you would need to do is substitute 0 in for all the x's. So in the denominator, we would have 0 minus 0 minus 6. In the denominator, we would end up with -6. But in the numerator, we would have a 5. So when you divide those two, you'll end up with a -5 over 6. So let's plot those points over here on the coordinate plane. So no x-intercept, so I don't have to worry about that. The y-intercept is 0, -5 over 6, which again is like right there. All right. Next, vertical asymptotes. So I think this will take just a slight explanation. If you notice that there is a quadratic expression, a quadratic polynomial in the denominator, you need to set it equal to 0 still and solve for x. But what happens with this particular example is that you would have to factor the denominator to be x minus 6, x plus 1 would equal 0. From there, you can see that I messed up the signs horribly, and I need to change those. So if you set x minus 6 equal to 0 and solve for x, it would be x equals +6. And if you set x plus 1 equal to 0, you would see that x would be equal to -1. Lastly, for the horizontal asymptote, you can recall that if there are no x's in the denominator, or in the numerator, or rather if there are no x's in a polynomial, the degree here is 0. The degree in the denominator is 2, so we would call this bottom heavy. And when a function is bottom heavy, when a rational function is bottom heavy, the horizontal asymptote will be y equals 0. So let me get these plotted over here. So here are the two vertical asymptotes. Vertical asymptote at x equals -1, vertical asymptote at x equals 6, and the horizontal asymptote at y equals 0. Now we find the domain. And we know that, and you can see on the graph here already, that -1 is to the left of +6. So we can allow x to be any number to the left of -1. We can allow x to be any number between -1 and 6. And we can allow x to be any number bigger than 6. So you don't even have to write down x cannot equal x can. You don't have to write down the domain over here like I've been doing. You can just write it right above the function, as I did here. Remember, each vertical asymptote will have a union over it, and then you will fill in as many intervals as you need to, one on each end, and then if you need one in the middle, you'll fill one in the middle. Now, we have to just do a quick visual check. Do we have a point already plotted in this interval somewhere? No. So we will have to find a point here. Do we have a point plotted in this interval somewhere? Oh yeah, here. It's the y-intercept. Do we have a point already plotted in this interval to the right of this vertical asymptote? No. So in this case, we need to find 2 points. So I need to pick any value that would be, any x value that would be to the left of -1. Why don't we pick -2? So we can find f of -2, and that would be 5 over -2 squared minus 5 times -2 minus 6, which would give you 5 over 8. So this was our x and this was our y. So I will plot that point. -2 comma 5 over 8 would mean I go left 2 and up a little bit, not quite to 1. So our point would be right about there. And I would do something very similar over here because I don't have any points graphed to the right of this vertical asymptote. So how about I pick 7? That sounds good. I'm going to use blue for this one. F of 7 is 5 over 7 squared minus 5 times 7 minus 6, which is equal to 5 over 8. Well, that's very interesting. So if I start here and go right 7, that's what the x value I picked is. The y value that corresponds with that is positive 5 over 8. So right 7 up 5 over 8, right about there. All right, I have a point in each of my intervals. Between -infinity and -1, I have a point right here. Between 1 and 6, aka between these two vertical asymptotes, yeah, I have a point right here. Between 6 and infinity, aka to the right of this vertical asymptote, I have a point right here. Now we can start graphing. So I'll just come in here from this point here. I can do this and this. There we go. From the point 7 comma 5/8, I can do something similar. There it is. Now with this point, and we have not breached this topic yet, this point, we would have a graph that would get close to this vertical asymptote, close to this horizontal asymptote, and then close to this vertical asymptote here. It almost looks like a parabola, or a polynomial that would be opening down. And that is because at no point are we going to cross this horizontal asymptote. If we were going to cross this horizontal asymptote, that would mean, since the horizontal asymptote is on the x-axis, that would mean that we would have an x-intercept. We do not have any x-intercepts because there are no x's to solve for in the numerator. So this graph would just open down. Let's take a look at what happens when you have an x-intercept and a graph crosses a horizontal asymptote. And this will be the last function here. So we have h of x equals 14x plus 4 all over x squared plus 4x. And all of this information was given in the previous slides when I was covering how to find x and y intercepts, as well as vertical and horizontal asymptotes. So here's all the information we need. But I want to draw your attention to something. What is very interesting here is that we have a horizontal asymptote at y equals 0 and an x-intercept. If a rational function has an x-intercept and a horizontal asymptote y equals 0, the graph will cross the horizontal asymptote. So let me get everything plotted over here so you can see how this looks. All right, so here I have the horizontal asymptote y equals 0. Here I have the vertical asymptote x equal to -4 and the vertical asymptote x equal to 0. And hiding right here, I have the x-intercept. That is all of the information that we know. Now, the next thing that we normally do is we find the domain. That's going to be pretty simple here. It goes from -infinity to -4 union, -4 to 0 union, 0 to infinity. And now I need to make sure that I have at least one point on each interval graphed. And that's where this changes a little bit from all of the previous examples. We have this special case here where our rational function has an x-intercept and a horizontal asymptote at y equals 0. So the graph will cross the horizontal asymptote. Well, the problem is the graph could cross this way, or it could possibly cross this way. So I don't know which way it is going to go. So even though we have a point that is already graphed in this interval between -4 and 0, between -4 and 0, there's a point, that does not give us enough information. So we still, in this case, when you have an x-intercept and a horizontal asymptote at y equals 0, we still have to find a point that is not the x-intercept to graph along here. And when I say the graph will cross the HA, I am using the same word, cross, that we were using for the behavior of x-intercepts or behavior of zeros. So when we were graphing polynomial functions, we say, oh yeah, the graph would cross at that 0. That's exactly what's happening. This is the same type of cross. It will cross from being above to being below, or from being below to being above. Again, we don't know which way it will work, so we have to still pick an x value in the middle interval here. All right, so that means we are going to have to put 3 values into our function. Some x value in this interval to the left of this vertical asymptote, some value from this interval between these two vertical asymptotes, as long as it's not -2/7, which is what our x-intercept is, and we have to pick a value to the right of this vertical asymptote. All right, So here I have some work finding three values on all three different intervals, and they are all color coordinated. So in this interval, I underlined in black ink. So I did my work down here, which means I picked a number to the to the left of this vertical asymptote. I picked -5. And I picked -5 because I knew it was going to give me some super big value that was not going to fit on this graph, to point out that it is not always best to pick the number right next to the vertical asymptote. So you could have picked -6 and you would have gotten about -6. So sometimes it's better to go a couple away from a vertical asymptote just to make sure you will be on the graph. However, if you pick a value, an x value, that gives you a y value that is off the graph, it is okay just to mark that value just a little bit off the graph. You don't have to be accurate and try to put -13 way down here. So we have a point here in black ink. The middle interval here between the two vertical asymptotes I underlined in red. So I did the work here. -2, 6. There it is. In the last interval to the right of this vertical asymptote, I picked the x value 3 and substituted it into this function for all the x's and got about 2.2. So 3, 2.2. Roughly right about there. Now all we have to do is draw our curve. And remember, if you have more than one point in an interval, these will be connected. These 2 points over here will be connected. From there, we just have to get close to the vertical asymptotes and the horizontal asymptotes. So to start with the left branch from -infinity to -4, it will look something like this. For the second branch of this function, between -4 and 0, it'll look something like this. Again, not perfect, but it gets the idea across. Lastly, for this last dot over here at 3, 2.2, we just have to get close to the horizontal asymptote and close to the vertical asymptote, and you've drawn your graph. Again, one of the things here for doing this example is to show you that the graph will cross the horizontal asymptote if the horizontal asymptote is at 0 and you have an x-intercept. Literally crosses like we were doing with the polynomial graphs. It's above the x-axis, and at that 0 it crosses over to being below the x-axis. I very much hope this video helps you in your understanding for rational functions. Good luck.